So there's one more theorem that I feel like we would lose so much stuff if we didn't go over it. This is from high school. So this theorem is about, of course, circles. So suppose you have a circle and you pick, on the circle, you pick 2 points. Then these 2 points, you can connect it with lots of points on the circle. This would be one. This would be another one. And so we can think of these angles as angles drawn to this arc. That's what we started with, 2 points. We start with these 2 points determining this arc, and then with any point on the circle, we can draw this angle. And so the theorem states the following. All of these angles have the same measure, absolute same measure, and they're exactly half of the single angle we can create when we connect points A and B with the center. I believe this is called the central angle. And these other angles are called the inscribed angles, but you're going to catch me sometimes calling it the outer angle, which is, I shouldn't. All right. There is a really interesting special case of this. I want to start with this, and then we'll prove the general case. I was just surprised that actually the special case is easier to prove than the general case. So let's get over that one. Maybe I should draw it there too. So suppose we pick an arc. This here, let this be our AB arc. And then the central angle, that's unique. You have to connect the points AB with the center. And this is the angle. And now if you connect A to any point in the circle and then B, that angle that we create here is going to be half of this. But now I'm going to show you a special case of it, which is, all right, usually an angle has 2 half lines or rays forming it. But let's start with 1 point we start, and we connect the 2 endpoints of the arc. So that's kind of weird. And then from either point, the other line is going to be the tangent line. All right, let's see. This is going to be surprisingly easy to prove. So let's call this angle alpha. And then this angle here has to be 90 minus alpha, because remember, the tangent line is perpendicular to the radius drawn to the point of tangency. And so if this is alpha, this has to be its complement, 90 minus alpha. But we are in a circle. So this line segment and this line segment are both radii in the same circle. So they're equal. So we're talking about an isosceles triangle. So the angles opposite the equal sides are also equal. So this is also 90 minus alpha. So when we add these two, what we get is 180 minus 2 alpha. I wonder what we have to add to that to get to 180, right? So that forces this to be 2 alpha. You can either see that the only quantity that we add to this to get 180 has to be 2 alpha, or you can say, let's call this beta just for a split second, and beta is 180 minus 180 minus 2 alpha, and then the distributive law, and you very quickly get that beta is 2 alpha. So that's kind of a weird case, and it comes up surprisingly often. And yeah, we can do a tangent line at the other point too. The proof goes the same way. So now for this general case, we're not going to do the whole thing. I'm just going to sort of give you the big picture. So let's pick an arc. It is arc AB. And then we're going to be a little bit circumspect about which inscribed angle to choose. We're going to go with this one. This is sort of a basic case where you see We have seen something very similar when we proved that this angle, if I connected it, would be 90. But this time, let's go and call this angle here alpha. If this angle is alpha, well, these two line segments are equally long because they are radii in the same circle. And therefore, the angles opposite those sides are also equal. So this one is alpha as well. And okay, then this has to be 180 minus 2 alpha. And now what do we have to add? So this is 180 minus 2 alpha. This is an angle to which when we add 2 alpha, we get 180. And then we add something to get to 180. That has to be 2 alpha. We proved the central angle, inscribed angle theorem for this special case when one of these line segments is actually a diameter. But that doesn't always have to be the case. So let's see sort of two less specific case. Oh, it would have been good to know. So suppose we don't have that special case, although almost. Let me go a little further so we will see something. This is the inscribed angle here, and this should be half of this angle here, the central angle. This angle is half of this angle. What we're going to do to prove this is basically we're going to take it back to this case. So we will say, well, we don't have a line that plays the role of the diameter, but let's just draw one. And then if you look at this arc here, based on that, if this is alpha, this is then 2 alpha. And if it's beta, then this is 2 beta, right? Looking at this other arc. And then guess what? This is alpha plus beta, and this is 2 alpha plus 2 beta, or twice alpha plus beta. So it's really not far from this basic case. But there is another situation which is also going to be derived to this basic case. So in this case, if you recall, the inscribed angle sort of included the center of the circle. And this is not such a case, right? If we connect this point with the center, that's going to be outside of the region determined by these line segments. But the basic idea is going to be the same. We're going to connect the center with this point, and then we're going to do the following. Consider this arc. Based on that arc, if this is alpha here, this is 2 alpha there, right? This is the central angle belonging to that arc. This is an inscribed angle belonging to that arc. And then it's going to be a little bit tricky. Let's look at this big fat arc here. Now the central angle belonging to this big fat arc is this big fat sector, basically. And to this arc, the inscribed angle is this one. So what that means is that this angle here is twice this angle. So if this is beta, this is now 2 beta. And then what we're interested is, here the angle we were interested in was the sum of 2 angles that were around this special case. Now it's going to be the difference, right? The angle we started with, this one here, is clearly beta minus alpha. And this one here is clearly 2 beta minus 2 alpha. Again, one of them is twice the other, right? So this yellow here is beta minus alpha. You see beta is the whole thing, alpha is just this part. And then around the center, same idea, 2 beta is the whole thing, 2 alpha is just this part. And when we subtract, we get what we're interested in. So that's 2 beta minus 2 alpha. So that's it. So now you've seen the proof pretty much for this theorem with central and inscribed angles. There's going to be lots of application, and some of them actually will touch upon our material in trigonometry. It's just kind of the teachers are supposed to bite our tongue and not to bring it up. But you're going to see that it pops up even in our trigonometry class with basic trigonometric proofs. It's going to show up. one more last thing. We have established the relationship between the central and inscribed angles, namely that the central angle is always twice the measure of the inscribed angle. Now, what if we apply this to a central angle of 180 degrees? If we select an arc that determines a central angle of 180 degrees, then to that arc, all the outer angles, to that arc, all the inscribed angles will be half of 180, which is 90. In other words, the Thales theorem is a special case of the inscribed central angle theorem, or another way to say the same thing is the inscribed central angle theorem is a generalization of the Thales theorem. So kind of a big picture here. Thank you for watching.